In the last lecture, we indicated that typically you as the analyst, you're interested, with the chemical information of, the test item that you're trying to analyze. Or in some cases, of course, you may be interested also with the physical quantity, things like pressure, temperature and so forth. Now, the instrument, on the other hand, hears, electrical information. So the instrument converts the physical or the chemical quantity into electrical information, which can easily, be transduced, through the instrument. And so every instrument, consists, of what you refer to as transducers. And transducers are the components that interconvert these data domains, from non-electrical to electrical, or from electrical to non-electrical domain. Any conversion from non-electrical to electrical domain is what is there for the input transducer. That's what happens first. And then the output transducer converts the information that's electrical into a non-electrical domain, which is the analyst, domain. Maybe I'll give you an example just to clarify what I've just said. Let's take an example of an instrument such as fluorimeter, which is typically used to detect, things like fluorescent compounds such as quinine in tonic water, for example. And just to remind you, quinine, that's a molecular structure. And as you can see, it's fairly conjugated. Remember, for a molecule to actually undergo fluorescence, it has to have electronic, conjugation. And you can see it is fairly conjugated, for it to allow for internal conversion as a so-called. And we're going to cover that, later on. Now, quinine, it's a molecule that is used against these kinds of species, protozoa species that transmit malaria. And it comes from the cinchona plant. To this day, actually, it's still naturally derived. Of course, people have tried to do synthetic processes to produce quinine, but none of it, is economically viable. And so to this day, people actually extract quinine from the cinchona plant, typically grown, in Peru and also some parts of Europe as well. Now, quinine, other than for the treatment of malaria, it's also used, I think, to treat things like the so-called restless leg syndrome. And you're also gonna see it, used in beverages as well, things like wines and so forth. I think it adds the flavor element. However, it should be added in very small amounts. I think up to about 83 parts per million, because it's a fairly toxic alkaloid. Now, so you've got quinine in tonic water that you want to detect by fluorescence. Now, if you look at the components, of a fluorimeter, typically, being a spectrometer, you've got a laser, which is the energy source. Remember what we said of the platforms of any instrumentation. You've got the energy probe, and then you've got the specimen, that is being studied. And then you've got, the responding detector. And all of us, all of that, we can call it, the detector. Now, in that case, of course, there are all those components in the detector. So you're going to see that the laser, which is a physical quantity, impinges on the tonic water and a response happens, meaning you get excitation of the electrons from the ground level to an excited state, and then after that, they relax back to the ground state, resulting into emission of a photon. And so in here, essentially, you still have emitted photon, coming from the tonic water. Now you can see here you've got what you call the phototransducer, and essentially that is, the input transducer. And you can see what's happening, with a phototransducer, as the name suggests, it's converting the photon into an electrical quantity. You can see that. So the phototransducer is converting the photon into an electrical quantity, in this case current. And you can see again within the detector you've got a couple of transitions there where the current is converted into a voltage using this Ohm's law relationship. You can see the voltage is proportional to current, with resistance being the proportionality constant. So in essence you just need to put in a resistor, and the current now it's converted into a voltage. Take note of this. Now each of these transfer function needs to be linear, meaning the current that I generate when I put it through a resistor, the relationship must be known, so that for any increase in current I get a proportionate increase in voltage. And of course you can see based on the Ohm's law that's what's happening in this case. It's a linear relationship. And then after that, you've got an output transducer, that converts, in this case, an electrical domain voltage, and it converts it, into a digit, that an analyst, can easily read. So I think you've seen, the process, for the input transducer and, the output, transducer in that case. Maybe another interesting example to consider for you to see these interdomain conversions within instruments is a thermocouple. And a thermocouple, I think, is the simplest, of the detectors out there. It's a thermodetector. Remember, it is based on this very old premise that if you join two dissimilar matters, two different matters, you connect them or solder them together, essentially you get a potential difference because of the differential conductivity, between metal 1, and metal 2. And, on one end of that joint, on the joint of the two dissimilar matters, you thermostat it, at 0 degrees centigrade, and then on the other end, that is the indicator joint, where you put it inside the sample that you're trying to detect its temperature. So you can see a thermocouple really, detects, temperature purely based on two dissimilar metals, joined together. Now, the conversion, and of course you can see this one is an input transducer again, the conversion of heat, which is a physical quantity, into electricity, it's based on this effect, called thermoelectric effect. And sometimes people call it, the Seebeck effect, which is based, on the person actually, who discovered it, around the 19th century. So it's a very, very old, premise. And as you can see, the temperature, gets converted, into voltage, because of, the thermoelectric effect. And so, now you've got, the voltage in that case, and of course you can easily digitize it, using, an appropriate, electronic digitizer to give you a number. And now that becomes, a number which is a non-electrical, quantity in this case. So you can see, the input transducer is a thermoelectric effect, the thermocouple, two dissimilar metals joined together, a very simple detector, and then you've got a digitizer at the end, converting the voltage into a digit. Sometimes, people always, would put in, things like a resistor, so that they can amplify the voltage. Like I said, the voltage relationship using the Ohm's law is, voltage is proportional, to resistance, rather, or to current, if at all you put a resistor in there. And so you can actually amplify the voltage that you get through a resistor to get current, and then you digitize, the current using an appropriate digitizer. Alternatively, if at all you're going analog, of course, you can still use a stepping motor on a pen, and you can use a chart recorder, using a dial, sort of to push, the motor of a pen if at all you're going analog. But of course, very few people these days, do analog, just because it's not as accurate, as using a digitizer. As I've mentioned before, any transfer function, of course, needs to be linear, be it what you're using to amplify the resistance in this case, be it, the digitizer. Any increase in one quantity should give you the proportional increase, in the next quantity. Now, I like to mention this, and I think you're always going to keep an eye on this. Some of these innovations that we say they are very, very old, are being reused or repurposed, to create new types of innovations. And so keep an eye on some of these things. That's how you start innovative businesses or technologies, by taking what is already known and transforming it or translating it, into new types of applications. I'll give you an example of somebody who's done something very simple, using essentially the thermoelectric effect. Somebody takes, a coffee cup, there's coffee in it and it's hot, and then they just put in a thermocouple, just simply solder two dissimilar metals, which converts the thermal energy, in the coffee, into a voltage or into electricity, and they can use it simply to charge their cell phones. And, these kinds of, ideas that you can get, from these concepts that we are learning, you can use it, towards solving other types of problems. And that is really what you call the art of innovation, taking what is known and possibly used for different applications and translating it into solving other types of problems. And so you can take a look, at that video, later on. Maybe another example to show you inter-domain conversions within instruments. Let's take an example of a simple instrument such as a pH meter. Now, a pH meter typically used, of course, to detect hydronium ions. And I think there's one student who'll be gonna be developing a pH sensor different from a glass membrane. We all know glass membranes, which are siloxane kind of crystals, are very good in capturing selectively hydronium ions. And so if at all you've got, a pH electrode, and you've got, the glass membrane, the glass membrane can capture, hydronium ions. And because remember, you create potential difference anytime there is a charge separation. If at all you've got two, maybe that's the container, you've got hydronium ions here, some of them get captured, by the glass membrane. If at all you feel, these glass membrane, with a known concentration of hydronium ions, say 3 molar HCl, and the one outside, it's unknown, then you're gonna create a potential difference, between what is inside and what is outside, through this interface. And in the potential difference, in the separation, in ion concentration across a membrane gives you a potential difference, and that gives you a voltage. So again, you can see that is an input transducer that converts hydronium ions in this case, which is a chemical, and converts it, into a voltage, just by having it captured, by a membrane. And then there's a potential difference between the inner solution and the outer solution, are separated, by that membrane. And if at all you've got a resistor, you can convert that voltage, into current. And as I've said before, you can just use a pen recorder if at all you're going analog. Otherwise, you can go digitizing using an appropriate digitizer. And again, that shows you the different type of interdomain conversion when you're making an instrument, such as a pH meter. As I've emphasized, you must make sure the transfer functions are known, so that the relationship is proportionally linear. Now, so you want to analyze something, and probably glucose is what you're interested in. And you're the analytical chemist, and possibly, you've got a glucose analyzer, but that is too big an instrument. And you've been asked, as the analytical chemist to design, possibly your own type of instrument. Of course, you can design things like a simple glucose meters, that are used, are very, very common. So maybe you've got a glucose meter, or even, you can decide I won't use blood. Instead, I'm gonna use tears, as a sample, and then probably using you can design, a sensor that can be probably put on onto contact lenses, and then you can simply detect glucose right on the contact lenses. And these days, actually, you can miniaturize, especially electrochemical devices, very, very small, such that, the contact lens actually has got, a glucose electrochemical sensor. And there's a couple of researchers, who are doing that as well. Alternatively, you can decide, well, I'm going to make an electrochemical sensor, that can go as a wearable, possibly as a smartwatch or whatever. And then you can use it, to detect things like glucose in sweat. So these are type of innovations, that are happening. Instead of people using, the very invasive, type of samples such as blood, very uncomfortable to keep pricking, your skin to analyze for glucose. People use non-invasive, type of samples of biological fluids, such as tears, such as sweat, and so forth. But then assume now you've got these instruments that you have designed. What do you do next? What do you do next? Remember, the instruments give you a signal, and you're interested in the chemical quantity, such as glucose, and you're trying to determine the amount, say, of glucose in sweat, in saliva, or conventionally in blood. What do you do next? Remember, the next thing you do when you've got an instrument and you've got the problem, the sample, you have to calibrate. And I can't overemphasize enough, the importance of calibration. It is the crux of analytical chemistry. You cannot do analysis, without calibration. And so calibration really is a process of deriving the relationship, between the analyte concentration in the sample that I'm trying to analyze and the instrument's response. You're trying to get the relationship between, say, the concentration of glucose and get the relationship, to the signal, that you get. And of course, you want that relationship to be proportionally linear, okay? So it's very crucial, for all analytical methods. Very few analytical methods out there don't really need, analytical calibration. Things like coulometry, gravimetry, those ones you just need to tune the instrument, but you don't need, necessarily, to do the calibration of the analyte, for it to be proportional to the signal, because those ones give you absolute, they're absolute methods. But all the other methods, really, you really need to do calibration. And of course, most of us, you've done this in Chem 211. We beat it to death, and we're going to continue to do this. If you end up in the industry, again, this is all what you're going to be doing. Calibration, calibration, calibration. And I've said that it needs to be linear. If I'm doing spectroscopy, maybe absorbance spectroscopy, that is a signal. And it needs to be linearly proportional, say, to the concentration of ion, which is what I'm trying to analyze in this case. So you can only really determine the concentration of the unknown within the range that is linear and that is calibrated. And so this is a calibrated region, Okay, and you're gonna see this, that as you go further up in concentration, you get to a point where the relationship ceases to be linear. As you go down in concentration, you get a situation where the relationship ceases to be linear. Now, these regions, cannot be analytically useful. So you cannot really use them, for calibration because the relationship is not known. It's not linear anymore. And so you only use the linear region. And we're going to define this later on when you're discussing figures of merit, because calibration curves, are the crux, really, of figures of merit, or really defining the performance of an instrument. It's all based on the calibration curve. So let me emphasize something here. Now, we all know that all instruments have got some uncertainty. There's always some bit of an error associated with every single instrument. Now, of course, some instruments are a bit more erratic, meaning they are less precise, than other instruments. And we're going to talk again about that in the figures of merit when we are trying to compare different types of instruments, because every instrument has got a different type of error. And so sometimes you have to think when you're choosing an instrument, depending on the problem, what is allowable, confidence intervals and so forth, okay? But remember the following, we are assuming in your calibration that any error that you have is because of the y-axis, which is a signal. As I've said, every instrument has got a bit of an error. So the error largely, should be on the y-axis, which is a signal. Now, we assume that in the x-axis, that this one is error-free, meaning you prepared the standards very, very accurately, and any error that you are getting, of course, there are error bars there. Any errors that you are getting, is because of the y-axis, the instrument, in which, of course, there's nothing that you can really do about it because every instrument, is erratic. However, you can quantify the amount of error. So take note of that, that there should not be any error in the x-axis, meaning the standards should be prepared very, very accurately. That's what they make. That's what a standard means. The concentration is accurately known. Of course, there are students, who's gonna make, errors here, operational errors, and that should not be allowed, okay? There should not be operational errors, in the x-axis. And that's why you guys took, the Chem 211, so that you are taught very, very carefully, how to do gravimetric analysis, the weighing very, very accurately. You are taught how to do quantitative transfer and so on very, very accurately. And the purpose for doing all that, was to make sure that there is no error, in the x-axis at all. You are taught to even calibrate, things like pipettes, to calibrate, the micropipette and so forth. And that is the reason, so that you make sure that the concentration of the standards is very, very accurate. So take note of that. So you've done your calibration, and you're gonna realize that in some cases, while it's desirable for the calibration, say the regression coefficient, to be very close to 1, meaning you've got perfect linearity, sometimes you get situations, like this, where some of the data, ceases or deviates, from linearity, such as that data point. So what do you do if at all you've got that kind of a situation? You can see the importance of this, because if you keep that data point, now the regression the regression lines are very, very different. If I keep that data point, now you can see the regression lines, are very, very different, meaning the concentration of the unknown that you're gonna determine is very, very different, as you can see, because that's how you determine, that you've got the concentration of the unknown. You use the calibration curve to determine, the concentration, of the unknown. You've got rather the signal of the unknown. You've got the signal of the unknown, and then you use a calibration curve to determine the concentration, of the unknown. And so you can see that because you've got that data point here that deviates from linearity, that you're gonna get very different results. So I'm saying all this, to emphasize the need for you to always look at your data just to check if at all there are any outliers, and see what you need to do about that outlier, using the methods that I'm gonna show you, the Q-tests, the grab test, and so on. I'm gonna talk about that, in the next slide. Always look at your data for your calibration to make sure you've got the best possible linearity, which is sort of quantified using the regression coefficient. We should be very close to 1. So that is the Excel method, or rather that's a graphical method where you can actually visually, see, the relationship between the Y, which is the signal, and the concentration, which is the X. And of course, you can, have the regression equation, Y is equals to mx plus b for univariate type of calibration, meaning you've got a single variable. And if at all you now have the unknown, you can put the y as the unknown, the b is known, which is a slope, m is a slope, b is the intercept, and you can determine the x. Now, but you can also determine, your regression models. You can determine your regression models, without necessarily, doing the graphical method, okay? And that one is the so-called the least squares method, where you use this equation to calculate, your m, which is, the slope. And then you use this relationship to calculate the intercept. And based on that, then now you can determine, your regression equation. And with the regression equation, then you can determine, your unknown. So the advantage of doing this is because the method, is objective and doesn't have, systematic bias. Although in most cases, the least squares model is very similar, of course, to the graphical method, where you derive the model graphically. However, the disadvantage of using this type of relationship is the fact that you can't see your data. You can't see visually, how the data points relate to each other. And so I encourage all of us, to do both the graphical method so that you can actually visually see how the data relates, and also do the least squares method, because in most cases, it would be much more accurate, than the graphical method. However, they are often very similar if the data is not very imprecise. If the data is very imprecise, you get the least squares method deviating substantially, from the graphical method. And in that case, then you should use the least squares method to determine your unknown. Now, another huge advantage, of using the least squares method, and why you need to use both, is the fact that with the least squares method, you can determine the standard deviation of your measurement. Take note of this, and this cuts across, all analytical chemistry or all type of analysis out there, whether you're in psychology and so on. Any value you determine needs to have a standard deviation associated with it, because there's always an error, that is inherent in every analytical method. Okay. And so we should always have a standard deviation associated, with the measurement. The good thing with the least squares method, you can actually determine the standard deviation of your measurement using that relationship. And so I would expect all of us, to actually make sure that they calculate the standard deviation of their measurement. Another important thing I should emphasize is the significant figures, and students forget to do these, yet it's critically important. And so assume you've got a measurement such as this. You determine the concentration maybe of iron is 56.456 plus minus the standard deviation using that relationship. You got it as 0.556 ppm. Now remember that is wrong, because the standard deviation, and the average, they've got different, significant figures, and you didn't account for the correct significant figure. Remember, the first number in your standard deviation that is uncertain should be the last number, in your average. And so the correct way to represent these data, would be 56.5 plus minus 0.6, because that is the first place, that's the first number where you are uncertain. Remember, standard deviation gives you uncertainty. And so that's a number that is uncertain, meaning all these numbers don't mean anything, because beyond that number, then you're very unsure, of what those numbers really mean. And so that's a correct way of representing your data, using the correct significant figure. And I hope I'm fairly clear on that. Just to get more details on how these equations were derived and so on, you can check the calibration handout, which is already posted, on Blackboard. Make sure you understand what these variables mean, like the K refers to the number of replicates or repeats, of your measurement for the unknown. And I think the others are fairly straightforward. N, would refer to the number of data points and so forth. X, of course, is the concentration of the standards, and Y would be the signal, and so forth. So for your least squares method, as well as a calibration charts, I'm gonna give you a calibration template that you can use, which is already posted on Blackboard, and you can use it for all your labs, including the dry lab as well, which will be posted, fairly soon. Take note of this. The template is only meant to get you started, and so you need to understand what's happening on the template and modify it, appropriately, so that you can get the correct result. So don't just punching the numbers and whatever it spits at you, that's the answer. Make sure you actually know what's going on, within the template, but hopefully it gives you a place to start if at all you're not very familiar, with Excel, for example. Again, you can see, and I'm going to talk about this later on, you can use it for different types of calibrations, which I'm going to talk about later on. But again, all the least squares relationships or equations are inbuilt. You can see inside the template, the standard deviation, is equation is inbuilt as well. But of course, remember, you have to treat the data, appropriately, to get the correct answer. So you have numbers, that you've generated, from your calibration plot. You've determined the unknown and so forth. what more do you really need to do? Remember things like the descriptive statistics. Typically you report the mean plus minus, you report the mean plus minus, the standard deviation. Now, in some cases, and of course, the mean, refers to, the middle point right there, Now, that's a mean. In most cases, you would find the mean, is equals to the median. If at all, you've got a normal distribution. But if at all the distribution is not normal, meaning it's skewed, then you're going to see the mean is not equals to the median. So if that be the case, the data that is most accurate, would be the median. Okay? So what I'm saying is, for a non-normal distribution, the data that you should actually report for grading should be the median. If at all, the distribution is fairly good, then you should report, the mean as a correct data. This is especially important, if at all the standard deviation is very large, okay? This is what I mean. If the standard deviation is very large, that means the distribution, is is quite not normal, and so you should actually report the median, okay? So how do I know, the data, is fairly good? I look at the confidence interval, and as I've mentioned, actually, you look at the error. If the error is very, very large, then you should realize you've got a problem right there, and you should look at your data again. Of course, the error could be something, or the uncertainty could just be something related with the instrument. But if the error is very, very large, and of course, there are some instruments that give you very large errors, and others, that don't, you should again look at your data carefully to make sure that it's not an operational error, and you should realize that it's only, an instrumental error, that is nothing that is a random error, rather, that is nothing you can do about. In the event, I've got an outlier, okay, then remember, you should always look at your data and test the outliers, using, the outlier testing methods, the Q-test and, the Grubbs test and so forth. And that's what you're going to talk about, in the next slide very quickly. So the Q-test, look at this data set here. I'm analyzing nitrate, and I've got 8 measurements. And I look at this data set. Most of them look very good, but these data set appear, or that data, particular data 14.3 appears to be fairly anomalous compared to the others. And so I want to test, is it an outlier? And so you can use a Q-test, which is a very simple relationship where you take the gap divided by the range. Now, to determine the range, you need to organize your data in increasing or decreasing order, so that you can take the largest, subtracted, with the smallest, and that gives you the range. And then the gap is calculated, by taking the questionable data subtracted by the number that is most closest to 8 in magnitude. You can see, so again, you order the data in increasing, decreasing order, questionable data minus the data closest to it divided by the range, and that gives you, what you call the Q, calculated. And if the Q calculated, is less, than the Q from the table, which you can determine right from the table, N is a number of repeats, and you can take, say, 90 or 95% confidence, so long as you specify what confidence you are dealing with. You can determine the Q from the table, which in this case is 0.47. So you can see the data that I calculated, the Q is actually less than the Q from the table, and if that be the case, I should keep the data. I should keep the data. So it means in this case it's not an outlier. I should actually keep the data. Now, The other method to test the outliers is a so-called Grubbs test. And the Grubbs test, again, is a fairly simple relationship where you calculate the G based on this relationship, the questionable value, minus, in this case, the average of all measurements, including the questionable value, divided by the data distribution, the standard deviation. And you can see when I do that, I get my G calculated as 2.14. And then I determine the G from the table. There are 8 measurements. And I can determine, the G from the table, which in this case is 2.13. Now you can see in this case, actually, the G that I calculated, is greater, than the G, from the table. And for that reason, I should reject, the data. So you can see I've got a problem. The Q test tells me to keep the data. The G test or the Grubbs test tells me to reject the data. So which one should I use? So ideally, you should use the Grubbs test. The Grubbs test, is more robust and it's more reliable compared to the Q test because it accounts, you can see, for data distribution. So the Grubbs test, accounts for data distribution, and that's why it's a lot more reliable, compared to the Q test. So in actual fact, it's the one that is recommended by the International Standard Organization, and most companies that you go to, you would realize they've got these so-called ISO certifications, meaning they comply, with the international standard testing. And so they typically would use, the recommendations, of the ISO, and that's how they get certified. And so the Grubbs test, is actually the one that is certified by the ISO, and also is the one that is certified by these other international organizations called the IUPAC, the International Union of Pure and Applied Chemistry. So for Chem 311, I like as always, to use the Grubbs test, which is the most robust, and reliable. So maybe just to emphasize some more, you can see, always look at your data, look at these data that you generate, and you've got now 2 measurements, that seems to be an outlier. So sometimes you can have more than one outlier. And so in that case, you need, to sometimes test, both of them, using the Grubbs test and so forth. And you see the importance again of looking at your data. You've got 2 different models. And so if at all you cared not to, reject these data set, you're going to come up with very different, types of results. So always look at, your data. And as I mentioned, you can have multiple outliers, which can very severely, skew your calibration curve and essentially make the determination of your knowns very, very erratic. And so another very robust, way actually to calculate or to determine, especially multiple outliers, is a so-called recursive studentized residues test. Now, I wanted to include it here, but I decided to delete it. It's fairly mathematical and time-consuming. And actually, in practice, we actually rarely use it. So the good news is, and of course, it's beyond the scope of this course for me to go and show you the derivation of those equations and so forth. So I decided not to bother with it. But if at all you're interested and you're in statistics, you can take a look at it. But in practice, we actually rarely use it. We essentially just look at our data. And, we would discard the data points. Most likely, in this case, you would have screwed up without a doubt, because you can see most of the other data points are in line, meaning it's certainly an operational problem, okay? Especially for multi-point calibrations, and then when you've got 2 data points that are far off, it's always a problem, often in the in the x-axis, actually. It's something that you screwed up. And so for that reason, typically you would discard them, and then you would remake the standards again and then repeat the analysis, and often that would solve the problem. Now, if the outliers are down here, very low concentration, most likely the problem is you're getting to the limit of linearity, or maybe the limit of detection of your instrument. So but all the data is here, the outliers are here, or these outliers are here, you're getting to the limit of linearity, or you're getting to the limit of detection of your instrument. So typically you would just simply discard them, and you would focus on the region that is actually linear. And so the next lecture, I'm gonna now very quickly talk about the different types of calibrations, which you know well about. It's gonna be very quick: standardization, external calibration, and internal standard calibration. And very quickly we're gonna discuss why one is better than the other and which one you should use for specific types of problems, and then discuss, of course, how you determine the unknown when you're using those different types of calibration methods.